All right. Hi, everyone. Welcome to my first office hours of the semester. Today, we're going to be going over chapter one and probably most of chapter two, if not all of it. And then at the end, if there are anybody with Alex questions or specific questions, we'll go over that. Just as a reminder, I can't really control Alex, and I can't really pull up specific topics on my own because I cannot access Alex as an administrator, so I can't select specific topics for us to look at together. So if you do have any Alex questions, you're going to have to show them to me, and I can either make you a host, you can share your screen, or you can just ask me after the fact in the group meet chat. All right, so let's just jump right into chapter one, structure and bonding. So the first part, a lot of this stuff I wrote before for myself. So a lot of what we're going to be talking about today is just general orgo stuff. And so anything except C and H are going to be referred to as heteroatoms. So if you see me say, you're going to write everything except for heteroatoms as in the line angle formula, I mean anything that's not carbon or hydrogen. So for example, here, the nitrogen and the two oxygens will be considered heteroatoms, if that makes sense, because all the other the carbons and the hydrogens that aren't attached to heteroatoms, they aren't explicitly drawn as if it were a heteroatom. And that's the basis for the line angle stuff. And I'm gonna have to delete some stuff on these pages because I was writing some notes for my stuff earlier, or for myself earlier. So let me just delete a few of this stuff. So when we're talking about orbitals, it doesn't really have too much of an impact on this class, but in Orgo 2, orbitals are going to be playing a bigger role in a lot of the different mechanisms. But here, this is just the general gist of it, going back, thinking about orbitals and stuff. So we can have an sp orbital, an sp2 orbital, or an sp3 orbital. What this essentially means is that we're combining one s orbital with just a random number of p orbitals, whether that be 1, 2, or 3. So just sp1, you can say it too, but I prefer just saying sp, is combining one s orbital with one p orbital. sp2 combines one s orbital with two p orbitals, and sp3 combines one s orbital with three p orbitals. And the way that I like to determine if an atom is going to be sp, sp3, sp2, all that stuff, is I like to see how many connections does it want. So if we look at the periodic table up here, each one of these atoms, so I'm just going to ignore all these real quick, and I'm just going to look at this top row. Each one of these atoms want a specific number of bonds, and that can be determined through using the valence electrons. So we know that fluorine has 7 valence electrons, oxygen has 6, nitrogen has 5, carbon has 4, and all that stuff. And so to fill in the rest of its octet, which essentially means it wants 8 electrons in its valence orbital. And so to fill in that last octet, it's going to want as many bonds as it needs electrons to fill an octet. So for example, if we look at fluorine here, fluorine has 7 valence electrons. It needs one more valence electrons to make its octet. So it wants one bond. Oxygen, 6 valence electrons. It needs 2 more electrons to fill its octet. It wants 2 bonds, and then so on. The easiest to remember as far as sp, sp2, sp3 goes is probably carbon. But I'm just going to, okay, so somebody in the chat is asking, so is it specifically wants bonds, not electrons, like lone pairs? So yes, it could have lone pairs, but it prefers bonds because then that will give the atom a 0 formal charge. And we'll get into formal charge later, but just know that it prefers to have bonds over just regular electrons. because if you remember, if you have lone pairs that fill in that octet, it's going to have a negative charge over a neutral charge, which we will see later. That's a good question. Okay, and so then going back to the SP, SP3, SP stuff, or SP2, SP3. The way that I remember this as far as carbon atoms go is that the number of letters that there are is the number of electron groups you're going to have. So this has one S and one P. That equals 2 electron groups, okay? So that means our carbon is going to look either like this or like this, because it has 1, 2, 1, 2. And it's the same thing here. So sp2 has 1s plus 2p. So it's going to want 3 electron groups. So it's going to look like this, where that double bond can be any one of these 3 bonds here. Okay? And finally, sp3, that's what we're going to see most often. It's going to have 1s plus 3p. That equals 4 electron groups. Our C is going to look like this. Okay, so that's easy enough for C. But when we're looking at other types of atoms, like different heteroatoms, we can't use this this rule is not hard and fast for those electrons, or those atoms, I mean. When I see those other atoms, what I like to do is if they have the number of bonds that is the same as the number of electrons that it wants, so let's use oxygen as an example. Oxygen, we know, wants 2 bonds. If the oxygen has 2 separate electron groups making up those bonds, it's going to be sp3. Okay? However, when the oxygen looks like this, where instead of 2 electron groups, it has 1 electron group, it's going to be sp2. Okay? Does that make sense to everybody? If not, then I can continue going over it with another example. But I'm just going to continue going forward. If you have any additional questions, again, message me either through GroupMe or through web courses, and I'll help you with that. So I'm just going to do one more example just to make sure everybody's got it. So if we look at nitrogen, nitrogen wants 3 bonds. And so if those 3 bonds are separate electron groups, it looks like this. It's going to be sp3. If instead it has 2 groups, likely like this, sp2, and then a single group, like this, it's going to be sp. Okay? And then sometimes you'll be asked to determine which one, or like, let's imagine that you're given something like this, where we have just something simple, NH right here, right? Yeah. Okay, so what I'm going to do is I'm going to label each of these atoms with their sp, sp2, sp3. So we know that each carbon that has 4 full bonds is going to be sp3. And recall that when we're working with a line angle structure, every single carbon is going to have as many hydrogens as it needs to fill up its octet. So this carbon at the end here is going to have 3 hydrogens. This carbon here is going to have 2. And then the other 2 carbons are going to have none because they already have 4 bonds, and so they don't need any hydrogens. Okay, so let's label each one of these atoms as sp, sp2, sp3. This carbon here is going to be sp3 because it has 4 bonds, or 4 electron groups as bonds. This carbon here, this carbon is going to be sp2. Now, if you see a carbon with a double bond, you know immediately that's going to be either sp2 or sp. It's sp2 when it only has a single double bond. It is sp when it has 2 double bonds, like if we look up here, because of the number of electron groups it has around it. Here for sp2, like I said, it has 3 electron groups around it. So if it has a single double bond, then it's going to have 3 electron groups around it. If it has 2 double bonds, then it's only going to have 2 electron groups around it. And so then that makes it sp. All right, so let's move on. This one's going to be sp3 because it has 4 bonds. This one's going to be sp2 again. So now let's move on to the heteroatoms. First, we'll look at nitrogen. So again, like we said, this nitrogen here, if we drew it out in its full Lewis structure, it would look more like this, with the carbon right there, and then it has its lone pair. So if we look here, this nitrogen has 2 electron groups. It wants 3 bonds and it has 2 electron groups. That means it's going to be sp2 hybridized, okay? And so then if we look at this oxygen here, I'm just going to draw in the lone pairs just so we can see a little bit better. If we look at this oxygen here, it wants 2 bonds and it has 1 electron group. That's going to make it sp2. And finally, if we look at this oxygen and we redraw it just a little bit more clearly, it has 2 bonds, it has 2 electron groups and it wants 2 bonds. So this is just going to be sp3. Okay? And one more thing to note is that any hydrogen bond, so like hydrogen C, hydrogen O, hydrogen nitrogen, all of these, the hydrogen is going to give you a 1s bond. Okay? So sometimes a question may ask you, tell me what orbitals this bond is made up of. All that's asking is what is the hybridization of the 2 atoms that make up that bond. And so we would say that's an sp3, 1s bond, because the carbon is sp3 and the hydrogen is 1s. And if we look at this one here, if it asks us about this one, then we would simply say that's sp2, sp2. Sorry, that kind of got blurry there. So we would say that's sp2, sp2. Okay, so orbitals are not scary. There's one more thing to note about it, specifically with carbon, or well, I guess not specifically with carbons, but most of the questions that are asked about this are going to reference carbons more than any other atom. So the certain the certain hybridizations are going to have specific molecular geometries associated with them. sp is going to be linear. And if you recall, that's because, for example, carbon is only going to have 2 groups, and if those groups are going to stay as far apart as each other as possible, which is what they want, because it's 2 electron groups pushing away from each other, then it's going to be linear. sp2 is going to be trigonal planar for the same reasons, and sp3 is going to be tetrahedral for the same reasons. So if I gave you a carbon atom that looked like this, let's say this is oxygen and we have H here. This carbon is sp2 hybridized, so it's going to be trigonal planar. Okay, and so we'll just move on now. All right, so again, like I said here, atomic orbitals, you're not really going to need them as much as you in Orgo 1 versus Orgo 2. It's just sort of important for Alex, at least, to understand how the shapes work. So if it's 2px, then it'll be along the x-axis. If it's 2py, it'll be along the y-axis. If it's 2pz, it'll be along the z-axis, which is this line that runs through the middle of everything. Okay? Hold on, I got a cough. Sorry about that. So again, this is just talking about orbitals and shells, which is what actually causes the specific hybridizations, but we don't need to worry about that too much. Again, these are my own notes that I wrote for myself just for just before this, so I knew what I would want to talk about and everything. So now what I want to talk about is formal charges. So formal charges are a lot easier than I think. So I'm going to put F here. So for formal charge equals the number of valence electrons that something has minus the number of bonds that it has minus the number of electrons in lone pairs. So let's say we have something like oxygen. Oxygen has 6 valence electrons. And so let's say that this oxygen, for example, looked like this. So this oxygen has 2 bonds, I'm going to put 2b, and then 4 electrons in lone pairs. And so then the way that we'd figure this out, the formal charge equals 6 minus 2 bonds minus 4 electrons, that's 0. And that's why it prefers having bonds over lone electrons. For example, if instead the oxygen looked like this, and it just had an octet filled by electrons, then the formal charge would be 6 minus 8 because that's 8 electrons in lone pairs, and so then it would have a charge of -2, which makes it less stable. And so then that's why it prefers having 2 bonds over having 2 more pairs of lone electrons. Does that answer your question about why something like an atom will specifically prefer bonds over lone pairs?
Yeah, it does.
Okay, perfect. And it has all, so just to reiterate, they want bonds over lone pairs of electrons because those bonds will give it a formal charge of 0, whereas having lone pairs of electrons, that will give it a negative formal charge. And so then this tracks with all the other ones. So like here, nitrogen wants 3 because it has 5 valence electrons. So 5 minus 3 minus 2, that's 0, and so on. Okay, so Lewis structures, I'm gonna go ahead and skip over this since most of your Alex goes over Lewis structures, and that's probably the easier part of Alex. But essentially, Lewis structures is using lines to denote bonds. So what we're gonna be using in this class is more the line angle structure. Now to review the line angle structure real quick, I know I used it earlier. Oh, hold on, there was a question in the chat. It said, my Gen Chems teacher that said formal charge equals valence electrons minus lines minus dots. Yeah, that's a very valid way to think about it. And I personally like that because that's how I do it in my head. But yeah, that always helped me personally. Thank you. Um, what was I talking about? Oh, right, line angle structures. So if we're talking about line angle structures, essentially what they are, they're sort of a condensed Lewis structure. So let's say we had CH3, CH2, CH2, COOH. Okay? When we're looking at this, I'm going to break it down step by step so it's a lot easier to understand what the Lewis structure and how the line angle structure is going to look like. So the first thing I'm going to do is I'm going to break up each of these individual little parts here and connect them through lines. Okay, so CH3 connected to a CH2, connected to a CH2, connected to a COOH. And now I'm going to ignore these 4 or these other bits and just focus on this guy right here because this guy is probably going to be the most confusing one. So if I'm going to break that down, I know I have a C bonded to an O, bonded to an O, bonded to an H. So I know here that I have 1 C, 2 oxygens, 1 H. And I know that this carbon does not have a formal charge because it didn't tell me that it had a formal charge. And so what that tells me is that it has to have a double bond with one of the oxygens. So I'm going to move this oxygen up here so it's easier to see. And the reason why it has to have a double bond with that oxygen is because in the formula we see the oxygen is right next to the carbon, which is right next to another oxygen. It can't be connected to this hydrogen because it's so far apart, and so then that hydrogen is going to be connected to one of the oxygens. I know this seems really confusing right now, but just bear with me. So I know that the carbon is going to be attached to the CH2. It's going to be attached to at least one of the oxygens. And so for it to be happy with the bonds that it has to be double bonded to one of those oxygens and single bonded to the other, which is then bonded to an H. This specifically COOH, this is a specific function, something called a functional group, which is something that you're going to see a lot, but COOH is going to generally look like this most of the time. Okay? I don't want to say all the time because there's always exceptions in science and blah, 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 but this is what you're going to mainly think of when you see COOH. And so now I'm just going to write in the rest of this. So I have CH2, CH2, CH3. Okay? And so when I want to draw the line angle structure, I'm going to drop the H's that are attached to any carbons because again, like I said earlier, any hydrogens are implied on the line angle structure because they are going to be there to fill in any bonds that the carbon needs to have a full octet. So now I'm just going to draw C, 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 O, O, H. And so now we have our basis for our line angle structure. Now, when we're talking about a line angle structure, every single carbon is going to be either a point or an end. So here we have 4 carbons. So I'm going to draw that out real quick. So 1, 2, 3, 4 carbons. And so then I'm just going to draw a line. 1, 2, 3, 4. Okay? And so I'm also going to number these carbons over here as 1, 2, 3, 4. And notice here how the double bond O and the OH are bonded to that 4th carbon. So they're bonded to this carbon. So now all I'm going to do is I'm going to draw the rest of the connections. So OH and then a double bond to an O. And then that's how you draw a line angle structure if you've never drawn one before. It'll be easier to understand once you get more practice in it, but I assure you it's a lot easier than just jumping in with no idea. Okay? Okay. So this talks about formal charges, constitutional isomers. So the reason that constitutional isomers are so important is because the same molecular formula having 2 different molecular forms can be really, really important in things like biology and the way that they react. So if you look at ethanol versus dimethyl ether, just recalling what we know about acid bases, which one would be a better acid, ethanol or dimethyl ether? I'm going to be like Dora and give you a second to think about it. And then I'm going to tell you that it would be ethanol because this ethanol has an O attached to an H. So it can donate this H as an acid. However, on the other end, this dimethyl ether only has hydrogens bound to carbons, which are really, really bad at giving up hydrogens to be an acid. And so then that's why it's so important to know the difference between constitutional isomers and something like resonance structures, which we'll get into in like 2 seconds. But so that's why constitutional isomers are important. Constitutional isomers are the same molecular formula arranged in different ways in relation to their sigma bonds. And what a sigma bond is, it's just a single bond. So let's say we have a C single bonded to a C. This single bond is a sigma bond, okay? However, if we have a C double bonded to a C, that is a sigma bond. That is not sigma. That is a sigma bond plus a pi bond. A triple bond would be a sigma bond plus a pi bond. How I like to think about it is that at least one of these bonds in all of these is going to be the sigma bond. Okay? Okay. Oh, I should put 2 here. Sorry. Okay. And so now what we're going to get into is something called a resonance structure. So resonance structures only have pi bonds or lone pairs moving. And what this means is that a double bond or a triple bond can move, so like a double bond or a triple bond, and any lone pairs can move. Single bonds cannot move. Okay? So for example, let's look at this guy here. So here we see that we had a double bond right here, and then that double bond is right here. So we know that double bond had to come from somewhere, right? So let's just focus on where the double bond ends up. We know that the double bond ends up between the C and the N. So if you look over here, C and N. If we notice something here, there is an extra lone pair on that nitrogen that is gone when we make that double bond. What this is telling us is that that lone pair makes up this double bond. And so if I were to draw a line, like an arrow showing what happened in this resonance structure, I would draw a line from the lone pair onto the bond because that lone pair is being transferred to make a new bond. However, if we left this here, like if we left this carbon alone, then it would end up looking like this with 5 bonds, which is a big no-no. And so if we look at the beginning one, just like we looked at the end one, we can see that there's a double bond right here and there's an extra lone pair right here. And so then what happens is this double bond broke away and then went onto this atom, okay? Notice how I'm drawing my arrows from either a double bond or a triple bond, so just a pi bond, to either another bond or an atom. And I can also draw that line from a lone pair to an atom or a bond, but I'm never drawing it from the atom to electrons. This is because arrows show the movement of electrons, not the movement of atoms. Okay? Okay, so let's continue on. These are not resonance structures because we can see here, this OH sigma bond is no longer present right here. So that is not a resonance structure. These two are constitutional isomers because sigma bonds moved, and that is not associated with resonance structures. Okay. So resonance hybrids, what this is basically telling us is that the true structure of something is not one or the other resonance structure. It's actually a hybrid. And why this hybrid is so important is because that negative charge, so the negative charge that would be here, is not localized. So it's not in one place on one particular atom, and instead it's delocalized all across this molecule. And so if we were looking at electrostatic map, we would have so like let's say our electrostatic map looked like this. If they're localized, then all the electrons would be up here. If it were delocalized, then the electrons would be spread out all across here, which makes the atom or makes the molecule more stable. And this will lead into acid-base stuff. Okay, so rules for resonance structures. So one more thing to think about with resonance structures is they have to follow the octet rule, like I said before. So if we look here, this carbon has 5 bonds. That's a big no-no, again, like I said, because then it would have 10 electrons, which is more than its wanted octet of 8. Okay, and let's see, molecular geometry, we already talked about this. Okay, so bond length. The shorter the bond, the stronger the bond, essentially. So this is something that's going to come into play when we're talking about like acid-base stuff. But for right now, just keep the general rule that the more bonds that you have, the longer the bond. So let's look here. So this carbon has 4 bonds. So it has to share its electrons with 4 other stuff, and so then it's going to be relatively longer. However, here we see this only has 3, so it only has to share its electrons with 3 things, so its bond is going to be shorter. Here, 2, even shorter. And here we can see the increasing bond length goes along with the electronegativity, where it works a little bit like a magnet, where the hydrogen will be partially positive. That's what this symbol means, partially positive. And the fluorine or the chlorine or the bromine will be partially negative. And the more negative this other atom is going to be directly related to its electronegativity. And the more negative that is, then the stronger it's going to hold on to a partially positive hydrogen. Okay, and I think that's about it for this chapter. Okay, so one more thing. When you're drawing a line angle structure with a triple bond, you have to draw it in a straight line like this instead of as a crooked line like that, because the 2 carbons on either side of that triple bond are going to be sp hybridized, which means they're going to be linear, and so we want to draw them as linear. Let's keep going, and I think that's it. So are there any questions on chapter 1 before I move on to chapter 2? I'm just going to go ahead and open chapter 2 real quick. No? Okay, then I'm going to take a sip of my water real quick. Let me mute myself. Okay, so now we're going to get into chapter 2. Chapter 2 is all about acid and base reactions and how it works overall, as well as just a general introduction to how a mechanism works. So, let me see, am I at the top? I'm not at the top. So a lot of this beginning stuff isn't super important. It's just telling you how to tell the difference between a strong acid and a strong base, or a strong acid and a weak acid rather, using a pKa or using like a value that's given. What we want to focus on more here is how do we determine whether or not something is strong or weak when just given something like this and this. One thing I want to do real quick before we go into actually determine which one's strong and which one's weak is I want to draw out how the mechanism for an acid-base reaction is gonna work. So it says here that this is our base. That's our proton acceptor. So what that means, it's going to end up with a hydrogen over here, and then this guy is our acid, our proton donor, so it's going to lose a hydrogen over here. Okay? And so the way that this happens is that the electrons from the base are going to go over here and grab this hydrogen. And what that's going to do is that's going to make a new bond right here between the base and the new hydrogen. And recall that a base has to have an available lone pair, and that's because it's going to use that lone pair to grab the hydrogen. Okay? And so then what happens between the acid here? Because hydrogen can only have one bond. It can only have two electrons. So this bond has to break. And again, like we said, the hydrogen can only have two electrons. Those two electrons are already coming from over here. So this bond has to break towards the chlorine. And that's why it gets an extra lone pair right here. Okay, so that's just like the general mechanism of an acid-base reaction. A lot of the times you're going to see it written like this, where it's like HA plus B with a lone pair yields, hold on, let me do this. Let me write the back and the equilibrium arrow for this real quick because that's important, and my little uh, my thing has frozen. That's cool. Okay, there it goes. And so I'm going to write the equilibrium arrows here because acid-base reactions are always going to be in equilibrium. And so then we're going to get something like this. The acid now has a negative charge, and the base now has a positive charge. But notice something that that this side is net neutral, so it has a net zero charge, and the same thing is over here, a net zero charge, because the negative and the positive cancel out. So there was a question in chat. So when drawing curved arrows, you always go from base to acid. As far as an acid-base reaction goes, yes, because you're going from the electrons from the base to the hydrogen. Okay? And so the reason that the acid becomes negatively charged after the reaction is that it's gaining an extra pair of electrons instead of having a bond. And so again, we discussed earlier about how a bond makes an atom be neutral, whereas a lone pair is going to give it a negative charge. And so then the same thing happens here. I was going to say something, but I forgot. So we're just going to move on, I guess. So let's just continue on. So here's how we tell the acid strength using concentrations. And we're just going to skip past that because I don't like that very much. And we're just going to be looking at all of these effects that we talked about a little bit in class. So let's break down these effects real quick before we go into here. So the reason why these effects contribute to acid strength is because we're not looking at how stable the acid is with the hydrogen. We know that it's probably going to be pretty stable with the hydrogen if it can have it in the first place. What we're looking at is how well the acid will dissociate into its H plus and A minus forms, or acid minus forms, okay? Because the more stable this conjugate base, which is just what happens to what's left of the acid, the more stable this guy is, the more likely it's going to be okay with existing like this. So like let's say we had something really, so let's say we had I don't know, OH negative. If that hydrogen left, we would end up with something called O negative 2, which I don't know if you recall from your Gen Chem, but this is really, really unstable. So it's not going to want to lose its hydrogen. So it's going to stay like this and not donate a hydrogen and not act as an acid. Okay? So overall, what these effects are saying is that the more stable the conjugate base is, the stronger the acid. Okay? And one more thing to note is that the order that these guys go in is the order that this matters. So the first thing you're going to look at is the element that hydrogen is attached to, and if that's the same, then you're going to look at resonance, then induction, then hybridization. But just recall that the importance of these guys goes along with the number that we're introduced to them. Okay, so if we're looking at this stuff, I don't like how it's organized, so we're just going to skip to size real quick. Essentially what this means is that the bigger a atom is, the bigger that the atom that the hydrogen is attached to, the more stable it's going to be as a conjugate base. So the way that I like to think of it is like, think of like we have this little cup here versus like a big bucket. So this is our small atom, this is our big atom. If I want to put a bunch of water into here, it would like spill out everywhere because this guy's really, really small. However, here, this big guy can hold on to that water really, really well. If we think of this in terms of um, the base, or if we think the water in terms of electrons and the cups and bowls or whatever that I drew, the size of the atom, it makes a lot more sense because the bigger atom can hold a lot more negative charge a lot better than a smaller atom. That's how I always thought of it. If you're confused about it, just again, hit me up through GroupMe or just through web courses. And so then that's why size is so important. Now, what do you do if you're in the same row? So when you're in the same row of the periodic table, you've got like stuff like carbon, nitrogen, oxygen. These guys are all similar sizes. So how do we tell which element is more stable without that hydrogen? So the next thing we look at is electronegativity. So the more electronegative something is, the better it is at holding a negative charge as well. So let's say we had, so here's this nice guy. There's this nice chart here. We have NH2 versus OH. I'm going to ignore these other ones because whatever. So we're looking at NH2 versus OH, which is more electronegative, N or O? Oh, good job, guys. I'm so proud of you. I'm like Dora. So, O is going to be better at being on its own. So, if we're comparing the two acids here, NH3 versus H2O, we know H2O is going to be the stronger acid because oxygen is more electronegative and thus better at holding a negative charge. Again, a reminder, you only look at electronegativity when the atoms are of similar sizes, so in the same row of the periodic table. Okay, so the next thing we're going to look at is resonance. And how I think of resonance is, remember how we talked about before, how resonance causes the electrons to be delocalized across a whole molecule instead of being in one single place, like right there. So we talked about this earlier with resonance structures, and just to reiterate, if we have the negative charge just on one place, then it's going to be pretty not very stable because that negative charge is going to want to get rid of itself and attach to something that's positively charged. However, when we have a delocalized electrons, then there's less of a negative charge in one place, and so then there's less desperation in that one place to get another positive charge to cancel out. Oh, and one thing to note, if you see a carbon with a double bond connected to an oxygen next to another oxygen, there's gonna be resonance. One thing that I like to note is that if you see, like, let's say we had something like this. If the carbon, so I'm just gonna call this carbon 0. If the carbons right next to carbon 0 have a double bond, then resonance is possible. That's just sort of a rule of thumb if you're having trouble seeing resonance structures. The reason why this is because if we think about how, like, just in the Lewis structure. So let's say we had this guy right here connected to C, double bonded to, I don't know, other C, doesn't matter for this at this point, connected to an H. If this bond breaks, this carbon is going to have 3 bonds, it wants 4 bonds. So it goes and makes a double bond with this carbon. However, this carbon now has extra bonds. So what it does is it breaks the other bond, which then causes a lone pair to go on this guy. So that's just sort of how resonance works. Oh, can you repeat the rule? Okay, so somebody asked me if I can repeat my rule of thumb. So if you see a carbon double bonded to something, it doesn't have to be an oxygen, it could be a carbon or it could be whatever. If you see that guy double bonded to an oxygen, connected to another carbon that's double bonded to something else, there will be resonance. And that's because, like I said before, these two carbons in the middle here, they're both sp2 hybridized. So they both want a double bond. They do not care where that double bond is. So that double bond can be between the two of them, or it can be between two other things. So that's why they can have that resonance. Okay? And so then the next thing, and again, just to reiterate, the reason that resonance helps with, hold on, let me get rid of that little box there. The reason that resonance helps with the stability of the conjugate base is because it helps delocalize the negative charge away from one specific place on the molecule, which makes it more stable. Okay? And so then the final thing we're going to be talking about is induction. So when we're talking about induction, what we're mainly going to be talking about is electron loving, electronegative atoms. So if you look here, fluorine is super electronegative. It loves electrons. It really does. So it's going to try and pull all of the electrons in this atom towards itself. Okay? So when we're talking about induction, let's imagine we have this guy here. This guy does not have any electronegative atoms, so all the negative charge is just around this one spot. However, when we have electronegative atoms, those electronegative atoms are going to pull that negative charge away from that single spot and towards itself. So that, again, helps delocalize the negative charge away from one single space on our atom, or on our molecule, sorry. Okay? And so then that's why induction helps. Finally is hybridization. Usually you're going to see hybridization mostly when we're talking about carbons. I would not try and compare hybridizations for the acid strength when we're looking at oxygens or nitrogens. You only are going to really worry about it when we're talking about carbons. So let's compare these carbons. So let's label all of these carbons in this molecule. So again, I'm going to mark off all the carbons, which means all of the points or ends. And now I'm going to label their hybridizations. This guy's sp2, this guy's sp2, sp3, 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 sp, sp. And so what we're going to do here is we're going to figure out which hybridization is going to be more acidic. And the more S character that you have, like I've written here, the more S character you have, the more acidic something is going to be. So if we look at SP, just SP, we have one S versus one P, so we have 50% S. For sp2, we have one S versus 2P, that's 33% S, and finally sp3, one S versus 3P, that's 25% S. So we can see here that sp is going to be the most acidic form because it has the most S character. So if you look here, is blue or red going to be a more acidic hydrogen? The answer is blue because it's attached to an sp carbon, which has more S character than an sp2 carbon, so it's going to be more acidic. The way that this has to work is because of what the orbitals look like. So you can see here sp is a lot more squat than sp3 or sp2. So right now I'm just going to compare sp3 and sp2 because that'll be just easier. We can see here that sp is a lot more squat. It's going to be less angry, I guess, if you cut off a part of it because it's going to be relatively the same shape. However, if we cut off part of sp3, we're cutting off a lot of sp3, so it's going to be less happy, and that's why sp is more acidic. And that's hybridization for you. Here's an example. Which of the following compounds is the strongest acid? So again, we're going to look at our 4 different effects. The mnemonic that a lot of people like to use is ARIO, where A stands for atom effects. Oh, I spelled atom wrong. That's why I'm a science major and not an English major. R stands for resonance. I stands for induction. And then O stands for orbitals. Okay? And so first thing we're going to look at is the atom that these hydrogens are attached to. So this one's attached to a nitrogen, this one's attached to an oxygen, this one's attached to an oxygen. All three of these are similar sizes. So the next thing we're going to look at is which one's more electronegative. Oxygen is more electronegative than nitrogen, so we can totally remove A from being the strongest acid. So now these are the same atoms, so we're done looking at the atomic effects. So the next thing we're going to look at is the resonance effects. Just looking at these, I know that this guy is going to have resonance. Why? Well, because if we take away this hydrogen, I'm just going to redraw real quick. If we take away that hydrogen, we have two oxygens right next to each other, which means two oxygens with extra electrons. So the way that these guys can do, they can just sort of pass around that double bond. The double bond can move here, a double bond can move here, and we can get our one of our resonance structures. And then this guy also has one more thing here. It has a bromine, which is a really electronegative atom. So it's going to have a induction effect as well, which makes this guy the strongest acid because of induction and resonance. Okay? Okay. So predicting equilibrium position. So the way that we do this is we find which acid is the strongest and then go away from that. So I'm just going to ignore these two bases, and I know they're bases because they're negatively charged. What we're going to do is we're going to figure out which one of these is stronger. And this can be a little bit tricky because they look exactly the same, except this one has S and this one has O. I don't think you would have a question like this on your test because we didn't really talk a lot about sulfur, but recall that sulfur can have sulfur is bigger, so it's going to handle the negative charge on it better. So like if we drew the two resonance structures, oh, I'm sorry, I totally skipped over that. Both of these are going to have resonance structures because they have something with a double bond right next to something that can have a double bond. Okay? So like the other form for each of them would look like this and this. And using the stuff that we talked about before, sulfur is going to be better at holding that negative charge because it's bigger. And so then this guy is our stronger acid. So the whole equation is going to go away from him and towards the left. Okay? I know we discussed this during class, but I just wanted to reiterate what Dr. Dowdy said during class and everything. And yeah, so we're just going to continue on. So this is just like common acids and bases that you might see. Lewis acids, Lewis bases, it's going to be similar because remember how we said that a Bronsted-Lowry base is going to use its electrons to grab a hydrogen. So it's going to use its electrons here to grab a hydrogen. And then a Bronsted-Lowry acid is going to gain the electrons from that hydrogen bond that it used to have. So what's happening here is that you can think of as these electrons are getting lost, quote unquote, and these electrons are getting gained. So here we can see the base donates a lone pair to our acid, which is the Lewis acid Lewis base model. Okay, so I'm just going to call that for chapter 2 now, and I'm going to open the floor for questions and any Alex questions that you might have. And I'm going to mute myself to get some water real quick. Okay, I don't see any questions so far, considering there's only like 3 people here, which I understand y'all are busy. I don't hold it against you. That's why I record these and post them to YouTube. Oh, okay, so somebody does have a question. I'll just give them a few minutes to write. But again, you guys do not have to come to my office hours if you cannot make it. I understand y'all are busy. I'm pretty busy too. And so I'm going to always post these on YouTube as long as I remember. So like right now I'm recording this one and it'll be recorded to my computer and then I'll upload it to YouTube for you guys to watch. Okay. It's no problem. Thank you for the kind words, but I mean, I feel like this is what I'm supposed to do as a TA instead of just sitting in class and playing Animal Crossing while the class goes on, which I kind of do. But I like to have a little bit extra help. So I'm gonna go ahead and stop the recording real quick. Just pause the recording, just so I can just wait for this question to come up. Okay, so we had a great question about how to know if something's a Lewis acid and a Bronsted-Lowry acid, or if something's a Bronsted-Lowry base and a Lewis base. So essentially, when we're going to compare Lewis bases to Lewis acids, Lewis bases to Bronsted-Lowry bases, for example, they're going to look like very similar. All that you need to have to be a Lewis acid and a Lewis base or a Bronsted-Lowry base is a lone pair. So a good rule of thumb is if it's a Lewis base, then it's going to be a Bronsted-Lowry base. Acids are a little bit different because to be a Bronsted-Lowry acid, you have to have that hydrogen. And so Bronsted-Lowry acids will be Lewis acids, but not all Lewis acids will be Bronsted-Lowry acids. All that means is that your acid has to have an availability for a new bond or lone pair. That can mean it's positively charged or it has a hydrogen. Does that answer your question about it?
Yeah, it did.
Okay, perfect. All right, so I don't think there are any more questions. I said we could go over Alex if you guys want to. If not, then I think I'll just end it there because we've been going for about an hour. But yeah, so thank you all for either coming or watching my office hours. Yeah, so I'll see you guys next time or before then if you guys need any extra help. All right, thank you. See ya.
Thank you.